Hello everybody, and welcome to the second half of our discussion of solutions. Last week we covered gases and the first part of solutions, where we got up to the concept of molarity, which is a concentration unit that indicates the number of moles that are dissolved in a liter of solution. So we will start out today talking about the ways that you can use molarity to simplify calculations in chemical reactions, and also in the description of solutions. And then I am going to move on to chapter 11 in a second lecture for this week, which will begin the discussion of reaction rates and chemical equilibrium. That topic will unify the topics of chapters 9 and 10 and move us into the final and most difficult section of our course, which is acid-base chemistry, which will require all of the knowledge that we have gained so far to understand. So this is probably the most difficult math that you will encounter this semester. It's still just algebra and arithmetic, so there's no need to worry. And we're going to go through lots of examples. So to start out today, we're going to talk about molarity and then the different ways that it can be used to describe solutions, and then we'll move on to chemical reaction rates. So the first example we're going to talk about today: what is the molarity of a 0.5 liter solution of sodium hydroxide if it contains 6 grams of sodium hydroxide? So the way that we go about solving a problem like this is we always start by stating our given and needed quantities. So we are given that we have 6 grams of sodium hydroxide solute, and we have 0.5 liters of the solution. And we need to find the molarity, which has units of moles per liter. Now we know from our periodic table that 1 mole of sodium hydroxide has a formula mass of 40.00 grams, which means that we can set up a number of different factors to assist us in calculations. So 1 mole of sodium hydroxide per 40 grams of sodium hydroxide, and 40 grams of sodium hydroxide per 1 mole. Now the appropriate factor to use in this case is the one with 40 grams in the denominator, because we have grams in the numerator here. So 6 grams of sodium hydroxide divided by 40 grams per mole is equal to 0.150 moles of sodium hydroxide. Now we have the number of moles, and we know how many liters we have, so we write our formula for concentration. M is equal to moles divided by liters, and we substitute our values: 0.15 moles, 0.500 liters, and we end up with a 0.300 molar solution of sodium hydroxide. It's pretty straightforward so far. So here's another example. What is the molarity of 0.225 liters of a potassium nitrate solution, which contains 34.8 grams of potassium nitrate? Now, this is a multiple choice question, but we'll go through the answer step by step. You start with 34.8 grams, and you know that potassium nitrate has a formula weight of 101.11 grams, and that's gotten by adding the mass of potassium, the mass of nitrogen, and the mass of 3 oxygen atoms. And we can set up our conversion factors here, and we set up our equation. Then we have 34.8 grams of potassium nitrate, and we divide by 101.11 grams per mole, and this gives us 0.344 moles. And then we set up our equation, divide moles by liters, and in this case 0.344 divided by 0.225 is equal to 1.53 molar. So that answer is B. So this is a summary of the types of solubility units we've talked about so far. And just to sum up, we have mass percent, which is mass divided by mass. That's the mass of the solute divided by the mass of the solution. And both of those have units of grams. Then we also have volume percent. So that is the volume of the solute divided by the volume of the solution. And those both have units of milliliters. Then we have mass over volume percent, which consists of the mass of the solute divided by the volume of solution. That has units of grams per milliliter. And then molarity has units of moles per liter. You can see how all of these would have their own applicability based on the conditions that you're preparing the solution. So molarity can be used as a conversion factor, and this allows us to make calculations of solutions. So, for instance, if you have 3.5 molar hydrochloric acid, HCl, that means that 1 liter of solution will contain 3.5 moles of hydrochloric acid. This is handy because you can scale this up and down and the numbers remain proportional. So, here are some conversion factors from those concentration units that we talked about. So the first line here, 10% mass concentration of potassium chloride. This means that 10 grams of potassium chloride in 100 grams of potassium chloride solution. And the conversion factors are 10 grams per 100 gram or 100 grams of solution per 10 grams of KCl. If you have a 12% volume ethanol solution, that means that there are 12 milliliters of ethanol in 100 milliliters of ethanol solution. This is useful if you're measuring out solutions of ethanol in the lab, or if you're trying to count the number of drinks that you've had. 12 milliliters of ethanol will be present in 100 milliliters of solution, and 100 milliliters of solution will contain 12 milliliters of ethanol. 5% mass per volume glucose solution means that there are 5 grams of glucose in 100 milliliters of solution. This presupposes that the solvent is water, because 100 milliliters is often just taken as 100 grams. However, if you have a different solvent, then you have to account for its density. So 5 grams of glucose per 100 milliliter of solution, or 100 milliliters solution containing 5 grams of glucose. And then we have a 6 molar hydrochloric acid solution. That means that it has 6 moles of hydrochloric acid in 1 liter of solution. And the conversion factors are 6 moles HCl per 1 liter, or 1 liter per solution per 6 moles of hydrochloric acid. Now you can use these concentrations to calculate the mass or volume of either the solution or the solute. We, as always, start by stating our given and needed quantities, and then we write out a plan to calculate the mass or the volume. Then you write equalities and conversion factors that you're going to need along the way, and then set the problem up and calculate. So we're going to go through this by doing an example. How many grams of sodium hydroxide are needed to prepare 75 grams of a 14% by mass solution? So there are a number of options here. We could have 10.5 grams, we could have 75 grams, or we could have 536 grams. So the way we figured this out, we know that we have 75 grams of 14% solution that we want to get to, and we need the number of grams to get there. So we write our plan, which means we have to convert grams of solution using the percent mass to grams of solute. We do that by knowing that 14% by mass means that there are 14 grams of sodium hydroxide per 100 grams of solution, which gives us the following conversion factor. And then we set up our problem. We have 75 grams of solution. We multiply this by 14 grams of sodium hydroxide per 100 grams of solution. The grams of solution cancel. So you have 75 times 14 divided by 100, which is equal to 10.5 grams of sodium hydroxide meaning that the answer is A. You need to use 10.5 grams of sodium hydroxide to make 75 grams of a 14% by mass sodium hydroxide solution. Here's another example. How many grams of aluminum chloride are needed to prepare 125 milliliters of a 0.15 molar solution? The options are 20 grams, 16.7 grams, or 2.5 grams. So the way we go about doing this, we know that we have 125 milliliters of solution, and we want that solution to have a molarity of 0.15, and we need to find out how many grams of aluminum chloride that requires. So we need to go from liters of solution to, using molarity, to grams of solute. So we have quantities we can set up here. 0.15 moles of aluminum chloride per 1 liter of solution is our conversion factor. And 1 mole of aluminum chloride is equal to 133.33 grams of aluminum chloride, based on the mass of aluminum and the mass of chlorine. So we get these conversion factors here. Now we set up our problem. We have 0.125 liters of solution. We multiply that by the conversion factor to convert from liters of solution to moles of aluminum chloride. So liters of solution cancel. Multiply 1.125 times 0.15. And then we also multiply by the formula mass to get the mass of aluminum chloride. Moles of aluminum chloride cancel. And we calculate it out to be 2.5 grams. So the answer is C. You need 2.5 grams of aluminum chloride to prepare 125 milliliters of a 0.15 molar solution. So now that we've fully discussed the nature of solubility and the different units that you can use to represent concentration, now we're going to talk about chemical reactions that happen in solution. So when chemical reactions involve aqueous solutions, we use the balanced chemical equation, the molarity, and the volume to determine the moles or grams of the reactants or products. I'm going to talk a little bit about this. So if we have a chemical reaction that we want that involves solutions, and we want to do calculations to figure out what mass of reactant or product we might be dealing with, we start by stating the given and needed quantities. We write our plan. We set up our conversion factors, and then we arrange our problem so that we can easily cancel units and solve. So here's an example. Zinc reacts with hydrochloric acid to produce hydrogen gas and zinc chloride. The reaction is here. Solid zinc plus 2 hydrochloric acid molecules yields 1 molecule of hydrogen and 1 molecule of zinc chloride that remains in solution. So the question is, how many liters of a 1.5 molar hydrochloric acid solution will completely react with 5.32 grams of zinc, leaving behind no zinc? We start by setting up our givens and our needed quantities. So we are given 5.32 grams of zinc, and we are given the molarity of the hydrochloric acid solution, which is 1.5 molar. And it's asking us to provide the number of liters of hydrochloric acid required to completely react all of the 5.32 grams of zinc. Now, this is a bit more complicated than the questions we've done so far. So the plan is 2 steps. First, we have to go from moles of zinc using the mole-to-mole factor to moles of hydrochloric acid. And then we have to use the molarity of hydrochloric acid to get to volume of hydrochloric acid. And it should be fairly straightforward to go from the mass of zinc to the moles of zinc because we know its formula weight. So 1 mole of zinc is 65.39 grams, and 1.5 moles of hydrochloric acid are present in 1 liter of solution. We also know that 1 mole of zinc requires 2 moles of HCl in order to complete its reaction. And so when we set up our problem, we have 5.32 grams of zinc. We know that zinc has a mass of 65.39 grams per mole. So we divide by that. And then we know that for every mole of zinc that is consumed, 2 moles of hydrochloric acid will be consumed. So we multiply by 2. And then we also know that there are 1.5 moles of hydrochloric acid in 1 liter of solution. So we divide by 1.5, which gives us 0.108 liters of hydrochloric acid solution required. So you need almost 110 milliliters to completely react all of the zinc. So here is a nice concept map that ties together what we've been talking about. So if you have a solid, it's usually measured in grams. You can use the molar mass to get to moles. Likewise, if you have a gas, you'll usually be given it in liters at standard temperature and pressure. So you can use a gas law to get to moles of that gas. And if you have a solution, you'll be given the volume. You will then use the molarity of that solution to get to moles. Once you've gotten to moles, you can use mole-mole factors to get to moles of your other chemical in your equation. And then you can use the same 3 concepts to convert to whichever phase of matter is required. Now that we've talked about concentration, we can talk about dilution. In a dilution, a solvent, usually water, is added to the solution to increase its volume and decrease the concentration. For instance, when you make orange juice from concentrate, this is a dilution. You put 1 can of concentrated orange juice along with 3 cans of water, and it produces 4 cans worth of orange juice, which is an homogeneous mixture. So in a dilution, we add water, we increase the volume, we decrease the concentration because the number of moles of solute remains the same. If the number of moles of solute remains the same, then increasing the volume must decrease the concentration. There is a relationship that we can use for this. So if the moles of solute are the same, that means that the concentrations and volumes are related by this equation C1V1 equals C2V2. So if you think about what the units of this are, concentration times volume equals moles, but number of moles are constant. So you can set both of these equations equal to each other and solve for the unknown variable. Sometimes C is also written as M if the units of concentration are in moles. Otherwise, it will be written as C for percent concentrations. So the concentration goes down because the particles spread out as the volume increases, shown here. And once again, we have another flow chart about how to solve problems involving dilution. So you can prepare a table of the concentrations and volumes, and then you rearrange the dilution expression to solve for the unknown quantity, and then substitute the known quantities into the dilution expression and calculate. And we'll go through this. So first, starting with molarity. What is the final concentration when 0.5 liters of 6 molar hydrochloric acid is diluted to a final volume of 1.0 liters? So first we prepare a table of the concentrations and volumes. We have the first concentration is 6.0 molar hydrochloric acid, and the 2 volumes are 0.50 liters and V2 is 1.0 liters. And we need to find the second concentration, the final concentration of hydrochloric acid. We know that the volume increases, and therefore we predict that the concentration will decrease. Then we solve our dilution expression for the unknown quantity, which is in this case the second molarity. So M1V1 times equals M2V2. Solving for M2, M1 times V1 over V2. Then we know the quantities that we're going to add to this expression. M1 is 6 molar, and V1 is 0.5 liters, and V2 is 1 liter. And so the liters cancel, and we are left with 6 times 0.5 divided by 1 equals 3 molar hydrochloric acid. Another example, using percent this time. What volume of a 2% by mass to volume hydrochloric acid solution can be prepared by diluting 25 milliliters of 14% hydrochloric acid solution? So we start by listing our known quantities. The first concentration is 14%, the final concentration is 2%, and the initial volume is 25 milliliters, and we need to find the final volume. We know that the concentration is decreasing, so we predict that the volume will increase. So now we rearrange our expression to solve for V2. So V2 in this case is equal to V1 times C1 over C2. And therefore, if we substitute our known quantities into the expression, V2 is equal to 25 milliliters times 14% divided by 2%, which is equal to 175 milliliters final volume. Next example, what is the percent mass per volume of a solution prepared by diluting 10 milliliters of 9% sodium hydroxide to 60 milliliters? So we start by preparing a table of our known values. Our first concentration is 9% mass to volume. Our first volume is 10 milliliters, and our final volume is 60 milliliters. And we need to find the concentration of sodium hydroxide that is produced by this. We know that the volume increases, and so the concentration must decrease. And then we rearrange our equation so that it shows the proper, we solve for the proper quantity, in this case C2. So C2 equals C1 times V1 over V2. And then we substitute our known quantities into the dilution expression and calculate. So in this case, C2 is equal to 9% times 10 milliliters divided by 60 milliliters, which equals 1.5% final concentration. Another example, what is the molarity of a solution prepared by diluting 0.18 liters of 0.600 molar nitric acid to 0.540 liters? Start with listing our known quantities. The first molarity, M1, is going to be equal to 0.600 molar, and the initial volume is 0.18 liter, and the final volume is 0.540 liter. We're looking for M2, and we know that the molarity is going to decrease, so that V is going to increase. Rearranging our equation, we need to know the final concentration, and so we solve for that. M2 is equal to M1 times V1 over V2. And substituting our quantities, we have 0.600 molar times 0.180 liter divided by 0.540 liter, which gives us 0.200 molar solution. Makes sense. The volume went up by a factor of 3, so the concentration needed to go down by a factor of 3. So now we get into the difference between solutions and something called colloids. So a solution is a transparent mixture. It does not separate, and it contains particles so small that they cannot be filtered out, and they also pass through semi-permeable membranes. So dissolved salts and also small molecules like sugars will all be part of solutions. Now a colloid has larger particles, usually nanoparticles or sometimes slightly larger. They also cannot be filtered because the particle sizes are so small. However, they can be separated by semi-permeable membranes. And the way that you can identify a colloid visually is whether it disperses light, meaning that it's opaque rather than transparent. So there are a number of different types of colloids in nature. Things like fog, clouds, or hairsprays are all liquids dispersed in gas. Dust and smoke are solids dispersed in gas. Shaving cream, whipped cream, and soap suds are all gases dispersed in a liquid. Styrofoam and marshmallows are gases dispersed in a solid. Mayonnaise and homogenized milk are liquids dispersed in a liquid. Cheese and butter are liquids dispersed in a solid, in this case protein. And things like blood plasma and paints like latex paint or gelatin, they're all solids dispersed in a liquid. Now, blood plasma is the part of your blood that is outside the blood cells. Now, there's a third type of mixture called a suspension. These are heterogeneous mixtures. They're non-uniform. They have very large particles that settle out of solution, and they can often be filtered. Generally, they must be stirred to remain suspended. Examples of this include things like platelets, or muddy water, or calamine lotion, all of which will separate over time and will need to be remixed. So here's a comparison of solutions, colloids, and suspensions. Solutions have small particles like atoms, ions, or small molecules. The particles do not settle, and they cannot be separated by filters or semi-permeable membranes. Colloids have larger molecules or groups of molecules or ions. They do not settle, and they can be separated by semi-permeable membranes, but not by filters. And then suspensions have very large particles that may be visible, which settle rapidly and can be separated by filters. And you may have all three of these present in any given mixture. Here is a visual example of, in part A, is just a mix of a solution, a colloid, and a suspension. In this part B graphic, they are pouring this mixture through a filter, which is catching the particles of the suspension while letting the colloid and solution pass through. And then in the C graphic, you have a semi-permeable membrane surrounding a aliquot of the solution, and it is allowing solution particles to escape, but not suspension or colloid particles. Now we're going to talk about the concept of freezing point lowering and boiling point elevation. So when you add solute to water, the physical properties change. Namely, the vapor pressure above the solution decreases because of a number of factors, including electrostatic interaction between the solute particles and water, but also by taking up space and that could be occupied by water molecules, which also reduces the boiling point of the solution, and the freezing point of the solution will also decrease. These are called the colligative properties, and they depend only on the concentration of solute particles. So the first one we're going to talk about is vapor pressure lowering. So if you decrease the number of solvent particles at the surface, this will decrease the rate at which they evaporate. The solute will often also cling to the water and create a binding energy that is more difficult to overcome, which will lower the vapor pressure as well. So boiling point elevation ensues because if you increase the concentration of non-volatile particles, this will lower the vapor pressure. And freezing point lowering, there's a couple examples of this that are really useful. Road salt, it causes the freezing point of water to drop below the normal freezing point, which leads it to be liquid instead of solid. When the particles of salt mix with the water, they hold them closer together, and as we all know, water, when it freezes, expands to form its crystal structure, and therefore more energy must be lost in order to do this, which causes the freezing point to lower. Another good example is the addition of ethylene glycol to water as an antifreeze in engines. This increases the number of hydrogen bonds in the solution, which lowers the freezing point and raises the boiling point. If you had just pure water in your radiator, it would boil away rapidly and cause problems, but the addition of ethylene glycol raises the boiling point up significantly higher than the temperature of the engine. So, now that we've talked about solutions and the concentration, we can talk about the specific particles that are present in a solution. So if you have a solute that is non-electrolyte, it dissolves as molecules, whereas if it is a strong electrolyte, it dissolves as ions. And if it's a weak electrolyte, it's somewhere in between. The solute in antifreeze, ethylene glycol, is not an electrolyte. Therefore, it dissolves in a 1-to-1 molar ratio. 1 mole of ethylene glycol equals 1 mole of ethylene glycol in aqueous. Sodium chloride, on the other hand, is a strong electrolyte, and it dissolves as ions in water. So sodium chloride solid goes to sodium plus aqueous plus chloride aqueous, which means that 1 mole of sodium chloride solid produces 1 mole of sodium and 1 mole of chloride for a total of 2 moles of particles. Now, there is a way to correlate this with the freezing point and boiling point alterations. You can see here the effect of solute concentration on the freezing and boiling points of 1 kilogram of water. You have pure water. It has 0 moles of solute particles. It has a freezing point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. Now, if you add 1 mole of ethylene glycol, which is a non-electrolyte, that means that there are 1 mole of solute in the solution. This depresses the freezing point by minus 1.86 degrees Celsius and increases the boiling point by 0.51 degrees Celsius. If you add 1 mole of sodium chloride, which is a strong electrolyte, it puts 2 moles of solute particles into the water and lowers the freezing point by 3.72 degrees Celsius and raises the boiling point by 1.02 degrees Celsius. And you're probably starting to see a trend here at this point. 1 mole of calcium chloride is also a strong electrolyte, and it produces 3 moles of particles because 1 mole of calcium and 2 moles of chloride per 1 mole of calcium chloride. This depresses the freezing point by 5.58 degrees Celsius and increases the boiling point by 1.53 degrees Celsius. So we can use this table to do calculations. Can calculate the freezing point, lowering, or boiling point elevation of various solutions, taking the assumption that for each 1 mole of particles, we'll depress the freezing point by a certain amount and increase the boiling point by a certain amount. So we start with our given and needed quantities. We determine the number of moles of solute particles, and then we determine the temperature change using moles of solute particles and the degrees Celsius change per mole of particles, and subtract the temperature change from the freezing point or add the temperature change to the boiling point. So the first example, we're going to calculate the freezing point lowering. In the northeastern United States, during freezing temperatures, calcium chloride is spread on icy highways to melt the ice. Calculate the freezing point of a solution containing 0.5 moles of calcium chloride in 1 kilogram of water. So we're given 0.5 moles of calcium chloride and 1 kilogram of water, and we want to find the new freezing point. So we know that calcium chloride dissociates to produce 3 moles of solute particles, and we also know how many degrees Celsius the freezing point changes when you add 1 mole of solute particles. So If we set our problem up, our temperature change is equal to 0.5 moles of calcium chloride times 3 moles of solute particles per 1 mole of calcium chloride times 1.86 degrees Celsius per 1 mole of solute particles. So we have arrived at the answer 2.8 degrees Celsius, meaning that this solution of calcium chloride will lower the freezing point of water by 2.8 degrees Celsius. Now, we're going to talk about osmosis. So osmosis is the process by which water flows across a semi-permeable membrane from a region of lower to higher solute concentration. This occurs because in a semi-permeable membrane, water can flow across it, and there is a force that occurs when the concentration is high on one side. There is an attractive force to the water molecules that pulls them through the membrane. This causes the water level to rise on one side of the membrane until the concentrations of the two solutions become equal, or an osmotic pressure is encountered, which stops the process. We'll talk about that in a second. But here is a semi-permeable membrane. You have water molecules on one side. You have water molecules plus solute on the other side. And the water molecules are attracted to the solute and act to bring the concentrations into equilibrium. I just mentioned osmotic pressure. So obviously, if you have pure water on one side and a solvent on the other side, it won't just pull all the water through, because water has weight and is being pressed down on by the atmosphere. And so in this case, when the atmospheric pressure is equal to the osmotic pressure of the water across the barrier, the flow will cease and remain in equilibrium. Now you may be wondering why this matters. Well, first, if you take this process and run it in reverse by applying pressure to the side of high concentration, you can purify water, even if it contains high amounts of salt, because if you provide a greater pressure than the osmotic pressure, pure water will flow back through the membrane and leave behind a high concentration salt solution in the region that pressure is being applied to. This is used in desalination plants on, say, the West Coast, where they routinely take seawater and pull the salt out of it to produce pure water. This process requires an immense amount of energy, but is probably one of the culminations of modern technology. Another use of osmosis, or the concept of osmosis, is in isotonic solutions, which are used in medicine to match the concentration of IV liquids with your body serum. So cell membranes in biological systems are semi-permeable, and osmosis is constantly occurring, either in the form of salt gradient, which establishes a concentration difference between sodium and potassium, leading water to flow across the cell membrane, or it could also be glucose in the case of mitochondria. And there are many other systems in which the concentration of salts is very delicate and must be controlled by osmosis. IV solutions are generally isotonic solutions, and they're designed to exert the same osmotic pressure as body fluids, such as red blood cells. They're usually composed of either a 5% mass to volume solution of glucose or a 0.9% mass to volume solution of sodium chloride, depending on your needs. So they're, in addition to an isotonic solution, which has the same concentration or same osmotic pressure as your body fluids, there are also hypotonic solutions and hypertonic solutions. In an isotonic solution, the red blood cell doesn't change in its volume. it remains normal. However, in a hypotonic solution, something called hemolysis occurs. So if the osmotic pressure is too low, water will flow into the red blood cell, which will cause it to swell and burst, which is not good. In the case of a hypertonic solution, it will suck water out of the red blood cell and cause it to shrink. And this is called crenation. So, hypotonic solutions have lower solute concentrations than red blood cells. This means that water will flow from the region of low solute concentration to the region of high solute concentration inside the red blood cell by osmosis, and this will cause the cell to swell and burst. And if the solute concentration is higher than red blood cells, then water will come out of them by osmosis, and that is called crenation. There's another use for osmosis called dialysis, where if you have kidney failure, they will take your blood and run it through a pump which acts as an artificial kidney. This artificial kidney consists of a semi-permeable membrane. This holds large particles like blood cells inside, but allows waste products like urea to be removed inside of a chamber of high concentration or low concentration. And usually this has to be done regularly because somebody with kidney failure can't do this process on their own. So here is a brief study check. Which of the following can be used to describe the four solutions given: isotonic, hypotonic, or hypertonic? So a 2% sodium chloride solution, a 1% glucose solution, a 0.5% sodium chloride solution, and a 5% glucose solution. So we just talked about what isotonic means for these. So 2% sodium chloride is hypertonic because a isotonic solution would be 0.9%. Glucose, 1% glucose solution is hypotonic because an isotonic solution would be 5%. A 0.5% sodium chloride solution is hypotonic because it is less than 0.9%, and 5% glucose is isotonic because that is the same osmotic pressure as blood cells. Here's another question to get you thinking. When placed in each of the following, indicate if a red blood cell will either not change, undergo hemolysis, or undergo crenation. So, first one is a 5% glucose solution, second is a 1% glucose solution, third is a 0.5% sodium chloride solution, and fourth is a 2% sodium chloride solution. So we just talked about all these. 5% glucose is, of course, isotonic, so there will be no change. 1% glucose solution is hypotonic, so it will undergo hemolysis. A 0.5% sodium chloride solution is hypotonic, and it will undergo hemolysis. And a 2% sodium chloride solution is hypertonic, so you will undergo crenation. Now that concludes our discussion of solutions, and I will separate the two videos, and the next video will talk about chemical equilibrium and reaction rates.